So, I mean, it's a great pleasure on our part to have Professor Behnia for our workshop. He has been one of the world's leader in, especially known for in the condensed matter experimentalists. He has been one of the leader among condensed matter experimentalists, especially known for his measurement of thermal transport in quantum materials. So, I mean, I guess the most direct connection with our topic for this workshop is that in many of the quantum materials, actually topological defects make a very significant contribution to the thermal transport. And this is one of the topics he's going to talk about today, the Nernst effect in superconductor in the vortex phase. So let us all welcome Professor Behnia. So would you please try to share your screen?
Do you see my screen?
Okay. Yes, it looks great. Okay, so let us all welcome Professor Behnia.
Okay. Thank you very much for your introduction, and thank you very much for the invitation. I'm going to talk about superconducting vortices. So it's a little, maybe it is connected to the topic of the conference, but I am an experimentalist, and I hope that what I'm going to present would be of interest to you. So this is a picture of my collaborators, both in my group and also in Stanford. We used samples coming from Harold Wang's lab and also from Aaron Kapitulnik's lab. So maybe I should begin with what I'm going to measure. As Professor Chong said, I measure mostly transport properties. So basically, when you look at heat and charge transport in a solid, they entangle in the sense that an electric current can produce a thermal gradient and a heat current can produce an electric current. And we know that these are connected. Actually, you have only 3 transport coefficients, not 4. This is known for a long time, and especially since Osage relations of 1930s. So basically, we have 4 vectors and 3 tensors. And normally, when we measure thermoelectric response, it is when we keep current equal to 0. What we are measuring is actually the ratio of these 2 tensors, which are alpha and sigma. Basically, this is what the experimentalists measure. Now, what I'm going to talk about is essentially the Nernst effect today. The Nernst effect is the ratio of a transverse electric field to a longitudinal thermal gradient as a function of magnetic field. It is normally 0 at 0 magnetic field, but what we measure is something which is this quantity, but you can then connect it to the off-diagonal component of the tensor alpha by looking at the fact that, so you have a few equations at the end, what we measure experimentally. If we have also the experimental access to rho xx and rho xy, the longitudinal and transverse resistivity, we can come up with the off-diagonal component of alpha. So one important point is that these 2 quantities have different natural units. The Seebeck coefficient, the Nernst coefficient, like the Seebeck coefficient, has a natural unit, which is the ratio of the Boltzmann coefficient to the charge of electron, 86 microvolt per Kelvin. But the natural units of alpha xy is actually a combination of the 3 fundamental constants, E kb divided by h bar. And what I can say in my introduction is that actually, when the Hall effect is very small, actually the ratio between these 2 quantities become very simple. Alpha xy is basically the conductivity times the Nernst coefficient. So you see, each of these quantities has its own natural units. So I'm an experimentalist. Just to tell you in a few minutes, in a few seconds, how we measure it. We measure normally the macroscopic samples. We have 2 thermometers. We have different types of precautions to keep the noise equal to 0. So this is the kind of noise level we achieve, in the sense that we have something which is of the order of nanovolt when temperatures can be well below 1 Kelvin. So it is just a very artisanal technique, in the sense that you have a lot of care to be done about wiring. Now, how did this story that I'm going to talk about begin? It began with a report in 2000 by the Princeton group, who found a large Nernst effect in underdoped cuprates. And this study identified this result with vortices. I'm going in a few minutes to say why. And the reason was, in 2000, people knew that mobile superconducting vortices generate a Nernst signal. But, and the reasoning was, since at that time, many people believed that in underdoped cuprates, you have preformed pairs. This gave rise to this interpretation that you have vortex-like excitations above TC. So this actually is something which we know is not correct. We now know that actually there are, so I'm sorry, I am going back because I think I am not presenting the right file. Okay. So now I go to this one. And so what I'm going to talk about today is actually this paper. So this is the story of how we came here. What we know in 2021 about the relationship between the Nernst signal and vortices. And as you will see, actually, we have a number of questions more than answers. Actually, somehow what was considered as a certitude in 2000 is now not at all something which is as sure as it was. So let me now begin by telling you, this is a slide that I prepared for this talk. What is a superconducting vortex? Actually, normally it is familiar to people who investigate superconductors. A superconducting vortex is a mesoscopic object, very much like a skyrmion, magnetic skyrmion, which has a complex structure. It has a normal core within the coherence lengths of the superconductor, and around this normal core, you have whirling supercurrents. So you have 2 length scales, the penetration depth, which governs the way the magnetic field penetrates your superconductor, and the coherence length, which governs the way the superconducting wave function dies at the center of the vortex. So you have a core. Around this core, you have superconductivity. But since you have a finite magnetic field, you have whirling supercurrents. And then finally, well far from the core, you will recover the superconducting density. Now, this vortex can move in 2 different ways. One way is the charge flow. The other is the temperature gradient. So my talk is mostly about the second way of making vortices move, that is to use a temperature gradient. The first one is much more familiar. So let's begin with the first one. In the first one, which is called flux flow resistivity, basically what you do is you put an electric current and you measure an electric field. The reason it happens is that superconducting vortex is a quantum of magnetic flux. It is an entropy reservoir. It is a topological defect. Now, for this effect, what you use is the fact that the flow of charge is going to impose a force on each vortices. This is the Lorentz force. The vortex moves normal to this current. You see, so the direction of the movement of the vortices is normal to the charge flow. So this is wrong. This is normal. And the movement leads to a transverse voltage which is in the perpendicular direction. Now,
excuse me, Professor Behnia, my apologies. There seems to be some problem. I mean, we are stuck with the first slide, slide number 3.
Sorry, can I, maybe I begin
Screen
again?
sharing having some problem, and somehow we have been stuck with slide number 3.
Sorry, I go back to my, yes, maybe I did something wrong. So here is, okay, so do you see my screen? Oh, no. Do you see my screen?
Yes. Okay. Yeah. It's not in the full screen mode, but I mean, I guess that,
yeah,
that can be.
We can only see the.
Oh, okay. Now
you see, you see everything. Oh,
yes.
Sorry about this. So, okay. So, but no, it doesn't work. So I'm obliged to stop the sharing because I don't know why. Okay. So normally, do you see my screen?
Yes.
Okay, sorry about this. So I was here, or did you see this part?
Yeah, we can see this. We can see your slide now.
Okay. So when what I'm going to talk about is what happens if you put a temperature gradient. If you put a temperature gradient, now what is going to happen is the thermal force on the vortex. Each vortex contains some additional entropy, and because of this additional entropy, there will be a force on this vortex, a thermal force. The vortex moves, and this creates a vortex. So these are the things which was known about the vortex movement, and I'm going to illustrate some experimental results. So back in 1994, for example, so this is one of the best sets of experimental data. You can see that when you look at resistivity of this superconductor, as you put a magnetic field, the resistive transition broadens, and concomitantly, you have a Nernst signal. So here you see the resistivity, here you see the Nernst signal. The same is true for another cuprate superconductor. Note that when vortices cease to move, they are pinned down. You enter the vortex solid region, both the resistivity and the Nernst effect become 0. And when you go to the normal state, both of them are going to become, the Nernst effect goes to 0, and the resistivity becomes the resistivity of the normal state. But note that even in this data, one can see that Nernst effect dies more slowly than resistivity becomes normal. Why? I don't understand why. Oh, okay. So I talked about this part of my talk. I don't repeat. And now I come back to this part. The whole point is that during the last 20 years, we have a good understanding of what is quasi-particle Nernst effect. Quasi-particle Nernst effect is basically something which scales with mobility. So contrary to what was believed in 2020, Nernst effect in a metal, in a common metal, is not necessarily 0. Actually, all these systems have been measured during the last 20 years. We can see that the magnitude of the Nernst effect actually scales with the ratio of the mobility to the Fermi energy. And this is something which can be well understood by semi-classical treatment. Actually, a way of looking at this is that the Hall effect, the low field Hall effect, which is semi-classical, is something which relates the quantum of charge, the charge of electron, to the quantum of magnetic flux. And this is the semi-classical expression for it. The Seebeck coefficient is something which relates the charge of electron to the Boltzmann constant. Again, you have a semi-classical expression in which you have the fundamental units and two length scales. The same can be said for the Nernst effect of quasi-particles. Basically, alpha xy relates its natural units to a series of material-related length scales. Now, there is a second story about the Nernst effect. It is about the fact that when you warm a superconductor above its critical temperature, the Nernst effect does not become zero. This is the Nernst effect due to superconducting fluctuations, similar to paraconductivity, Aslamazov-Larkin type of fluctuations. And this, we have a good theory for that, which was developed by several people. First by these three gentlemen in 2002, then it was developed by other theorists, and experimentally it has been approved. So I show the data from our group and also from Typher's group. Basically, we think that now we can understand why there was a superconducting Nernst effect above TC in underdoped cuprates. It comes from the fact that even in the normal state, you still have some fluctuation Cooper pairs because there are Gaussian fluctuations, and even above the ground state, the system knows about it. And the agreement with the theory is, I would say, excellent. Actually, it is one of the cases where you see that emanations of the BCF theory of superconductivity works very well. So here is the table, and here I come to the mystery. If you look at quasi-particles, basically, you know what is their entropy, you know how much magnetic flux they are carrying, and alpha xy is just the ratio of the two. If you look at fluctuations, short-lived Cooper pairs, again, each Cooper pair has an entropy of KB. It has a flux which contains this expression, and alpha xy is a ratio of the two. So how about superconducting vortices? We would expect that the magnetic flux is quantized, but the entropy depends on the vortex. It should vary from one superconductor to the other. And if we measure alpha xy, we have something which will give us something which depends on the superconductor in question. The question is now, how much entropy carries the vortex? Now, one surprise was that when we look actually how this alpha xy evolves as a function of temperature, when you cool down your system below TC, you see that you don't see any anomaly at TC actually. The two signals, you see this is a logarithmic scale. So the signal changes by almost 3 orders of magnitude. So this is the superconducting part. This is when, the fluctuation part. And this is when you have really a superconducting phase. And you cannot detect any anomaly from one to the other. Okay, now, the reason we became aware of the existence of an anomaly in our understanding was when we began measuring Nernst effect in this superconductor. So this paper first was motivated by looking at samples made by Harold Wang, which prepared 2D thin films, and we looked at resistivity and then look at the data for each magnetic field. So you see the field is small. This is 5 millitesla. You can resolve the Nernst effect and you can resolve resistivity. So in the normal state, there is some Nernst effect, but at these fields, this is very small. So you can clearly see that as we change the magnetic field, the two signals evolve. And finally, when you kill superconductivity with a magnetic field high enough, you lose it. So this was a rather hard experiment, but what was surprising, so we measured another sample. This comes from Kapitulnik's lab. This is a system, molybdenum germanium, which was used in superconducting insulating transitions. But what I would like to begin noticing is the amplitude of the Nernst effect. The Nernst effect in this system has a magnitude which is of the order of 7 or 8 microvolt per Kelvin, a little lower than the other guys. Now, what the picture which was emerging was a little surprising. We measured 2 superconductors with very different TCs, and we see that these superconductors, so the first one and the second one, I am showing the Nernst effect at different magnetic fields as a function of temperature. In the third one, I am showing the Nernst effect as a function of magnetic field for different temperatures. But what I would like you to notice is that while the temperature is different, the TC is very different by at least one order of magnitude, the amplitude of Nernst effect, the value of the Nernst effect, the maximum, is almost the same in the three systems. Now, this is not only about these three superconductors. We just looked at what was measured by anybody during the last 40 years, 30 years, in any superconductor, from something which has a TC of almost 100K to one which has a TC of almost 200 millikelvin. And what you see is that while the TC changes by 3 orders of magnitude, the amplitude of the Nernst effect doesn't change that much. It, of course, is not exactly the same, but it changes between 2 and 10. Okay, just after our paper was published, there is this paper by the Oxford group, and they measured another system in which they detected superconductivity fluctuations above TC. But one of the interesting things is that if you look at the signal of the Nernst effect, this is also comparable to what we are seeing in the same range of amplitude. Okay, why this is surprising? Actually, what would be the entropy of vortices has a very long history. This begins with Stephen in 1966. So you have Otter and Solomon, a paper by McKee, this paper by Clem, and basically all of this was visited. So now I'm going to focus on this paper, which was a paper much, in 2010 by Sergeyev and al. And actually, they already said that something is wrong about these theories, because the question was, what is a vortex entropy? Okay, the simplest way of thinking about this is, okay, to calculate the entropy, you take the derivative of your Fermi energy, your free energy of the vortices, and you end up by having something which is proportional to the slope of your HC1. And you end up by this, which depends on your penetration depth and the ratio of the penetration depth and the superconducting length scale. What Sergeyev suggested that this expression is not correct because it assumes that all energies present in the free energy are going to contribute to entropy. So their point was that actually you should make a distinction between electromagnetic energy and the entropy inside the core. And if you do this, actually you are going to revise downwise the entropy of the vortices. And they came with this conclusion that if you do this, you find this expression for entropy, which matches the experimental data shown by these symbols. The problem is, of course, it is not very hard to see why the transport entropy should have this kind of temperature dependence. Because at TC, there is no entropy difference between the two phases, the superconductor and the normal state. At 0 temperature, the entropy should go to 0. So somewhere in between, almost at half of TC, you should have a maximum. But the question is, how much should be this maximum? Here, what they are showing is basically arbitrary units. So, somehow this paper is very important because it detected that there is something wrong about the conventional theory, but at the same time, it did not actually give a quantitative account of experimental data. Now, what they said is correct in the sense that you would expect that you will have this formula for entropy per vortex. We can see why, because it is easy to see that the core has a volume which is proportional to the square of the diameter of the core, which is correlation length. And if you take this volume, you have some energy, which is basically the entropy excess would be the thermodynamic critical field derived by temperature. And this should scale with the size of the vortex. Now, one thing about the strontium titanate is that contrary to cuprates, it is a space superconductor. Everything about it is known. We know what is HC2, we know what is HC1, we know the Ginzburg-Landau parameter, and we know what is the critical field. And if you do this, you see that actually what theory expects and what the experiment finds are different by a factor of 50. Something is wrong. What was proposed theoretically is too large compared to what is measured experimentally. So the two numbers are here. You see that instead of having 10 minus 2 joule per Kelvin meter, we have something which is 2 10 minus 14 joule per Kelvin meter. So first of all, so here is a mystery because this is a superconductor about which we know everything because everything can be measured. The second mystery is that, as I said before, I'm showing data from different groups. It's not like our group. This is a measurement done in Japan, actually, in 1997. This is done in Grenoble, and this was done in my group long time ago. And you can see that in all of them, we can not have a Nernst effect which is larger than what we found in STO of the same order of magnitude. Actually, the mystery becomes more remarkable when you begin by calculating from experimental data your entropy per sheet. You end up by having a number. So, you know, the Nernst effect, if you look, are of the same order of magnitude, but they are not equal. Now, if you combine the Nernst effect and resistivity and try to deduce what is the entropy per sheet per vortex, you find a number which looks universal. Actually, within the experimental data, all these numbers are close to 10 minus 3 joule per Kelvin. And basically, this is the Boltzmann constant times logarithm, the natural logarithm of 2. So can it be that the peak mobile entropy per sheet is simply ln2? It's too early to say because, I mean, we have not studied all superconductors which are available. And of course, we have no theory for that. Now, the first reason we should scratch our head saying why the traditional approach to the vortex Nernst fails. And the second is, the first question is, okay, the assumption is that when vortex moves, it is going to carry all the entropy it stocks in the normal state with it, which is an assumption which can be actually revised, because you can ask the following questions. What is the fraction of the entropy stocked in the vortex when the vortex is static, which is going to move with the flux line? The second question is, well, is there any way to get this fraction equal to some very simple expression as simple as KBLN2? So I'm not going to give really convincing answers to these questions, but in the remainder of the talk, I am going to just propose how we can find a way out of this. You see, the first question, the vortex is actually not completely leak-proof, because in the experiment, in the Nernst experiment, actually you can ask yourself how much, what is the velocity of the vortex? The drift velocity is extremely weak. It is of the order of millimeter per second. We have an idea of what is the electric field you are measuring, what is the, you use the Lorentz force, and from that, you have a damping force at the end. Vortices are steadily moving, but this velocity is extremely weak. When you calculate how much time does it take from vortex to travel one coherence length, it is of the order of 0.1 millisecond, which is a very long time microscopically. During this time, actually, quasi-particles which are inside the vortex core and those which are outside the vortex core have ample time to mix up. So actually, you begin to ask how much entropy sticks to the flux line. You would expect actually to answer none, and then the surprising question is that at the end you still have a Nernst effect. So some entropy should still be there. But if you begin to think about these time scales, which I can justify, where does it come from? But I don't have the time to say it now. You can see that actually the vortex is leaking quasi-particles are going to change place between inside and outside the vortex, and it works. Now, why should there be still an entropy associated with the moving flux line? So for this, again, I don't have an answer. This is a question that our theorist colleagues should answer. But I would like to attract your attention to this work by Grigory Volovik, which made the first comparison between a black hole and a vortex. And the vortex he had in mind was a fermionic vortex, which can happen either in helium-3 or in superconductors. So this chapter of his book, The Universe in a Helium Droplet, is entitled Analogues of Event Horizon. And there he says that a black hole is a region from which an outside observer cannot obtain any information. And he bravely declared that actually analogues of this situation can be realized in condensed matter. And the simplest way is to imagine there is a liquid where you have velocities, where there is a boundary to the velocity in which you are going to exchange information. This velocity is not the velocity of light, could be something which depends on the matter you are looking at. And in that case, the inner and outer observers using quasi-particles to transfer information, they cannot communicate with each other. So now you go back to your vortex. Actually, the only information that you have about the vortex is that it's a vortex and it is not a non-vortex. This is the only way of thinking that at the end of the day, the only thing which survives when the vortex is moving is just one bit of information, ln2. Okay, this was just a speculation. I'm not aware of any work. So our work was published last year, and we are looking to theorists to come with this with an answer why there is such a discrepancy between the existing theory and the experimental results, and is there really an irreducible actually entropy for a moving flux line. Thank you for your attention.
Okay, thank you very much for your fascinating talk, Professor Behnia. So now the session is open for, the talk is open to questions. Okay, Dr. Burma, can you please go ahead?
Yeah, thank you for the nice talk. I have a question which may be not relevant to your this presentation, but I'm a theorist, so I'm just curious to know that how difficult it becomes to make the temperature gradient time dependent or oscillatory.
It is possible. We have not done any experiment in which the temperature gradient is oscillatory, but if you have any idea, yes, it is feasible. Why did you think that it is interesting to make an oscillatory temperature gradient?
Okay, it is actually there in 2015, around that there is a paper by Liang Fu. So there they studied this very curvature dipole induced Hall effect, like where for the topological materials who respects time reversal symmetry but inversion is broken. So then linear order basically this transport coefficient vanishes, but if you go to the non-linear regime, then in the basically non-linear coefficients, so this very curvature dependent.
Sorry, but this is very unrelated to what we are talking. No, this is about topological materials and resistivity, and I don't see the connection.
Yeah. I just asked about the that's why I said that I just asked about this time
Yes, you
dependent.
can. So yeah, the answer to your question is yes, we can modulate the temperature if necessary.
Yeah, sorry, it is not related to this. Yes, sorry. Thanks.
Thank you.
Okay, so we have next question from Segwan.
Thanks for the nice talk, Professor Behnia. So I have two questions. The first question is about this entropy of vortex per sheet. So you calculated this. You argue. You speculated that this vortex entropy per sheet is kBn2. But in your argument, after this calculation, doesn't involve this sheet, right? So if you, in order for you to be correct, I guess vortices in each layer should be independent.
Well, this is
right?
part of, no, you see, the per sheet is just the fact that when we have our measurement gives something which is joule per Kelvin per meter. Okay, so somehow, if I want to reason in the language of Boltzmann constant, you know, entropy, its units is Boltzmann constant. So is, you know, I should get rid of meter. So you see, so your question is excellent because there is a subtle point here. So I should find a length scale and divide my stuff by length scale because, of course, the bigger your sample is. No, what this length scale is, one case would be to take the coherence lengths along the third direction. If I take the coherence lengths, actually, I don't find this universality. The way I did it, maybe it is wrong, is to take the interatomic distance along the z-axis. So some of these, you know, it varies a little, not that much, but you know, one should find a length scale to divide it. So when I say per sheet, means per lattice parameter of the material in question.
Yeah, actually, it makes sense to achieve this highest peak in Nernst signal. I guess it's better to have independent vortices in each layer. Maybe that's when you have this maximum Nernst signal.
Yeah, but you see, they are not. You see, you have pancake vortices, but some of these superconductors, the vortices are not pancake vortices. So it is really three-dimensional. It's just that how do you go from 3 dimensions to 2 dimensions? You see, there is a. It looks like, you know, the problems. This is just a question of going to extend from an extensive quantity to intensive quantity, and you need some lengths. Our result seems to be there even for superconductors which are not 2-dimensional.
Yeah. How about this this fluctuation of this vortex line? That should contribute to entropy too, right? This fluctuation of this vortex line in the thickness direction.
Yeah, but you see, think about the way vortices move actually. So people have not imaged how vortices move. Vortices move like rivers. Of course, there are things, but they move together. Okay, so this has been, you know, the question is, what should be, you know, we know the equations, we know the Josephson equation, which give, you know, if you have the velocity, you expect some energy. Now the question is, why the thermal force on a vortex is so weak? It looks like the entropy, which is really mobile, is much smaller than the entropy which is static, you know. But again, if you begin by thinking about this, if I have a bag of entropy and this bag is full of holes, when I begin to move, actually most of entropy is gone. You know, it's something like that. So the paradox is apparent because up to now people have not thought about the fact that all entropy is not movable. Which would be interesting because the day people begin to think of entropy of skyrmions, I think the same kind of questions are raised. What is mobile and what is there.
Also, yep, the last question is, would there be any other experimental techniques that can measure this vortex entropy other than Nernst effect?
Good question. You can measure Eddington effect, but you see, so Eddington effect is when you put an electric current and you measure the transverse thermal gradient. Okay,
I
so
see.
but normally, so we can do Eddington effect in other transport measurement. But you know, if the two quantities are not equal, it means that the experiment is wrong because we cannot violate the Onsager relation. So, of course, but it is a good idea to measure also Eddington to see if the two quantities match.
Okay, yeah, interesting. Thank you.
Yeah, to the best of my understanding, Professor Behnia's past thermal transport lecture that he delivered before COVID in Korea has been public, and actually many people have been studying it. So I have been expecting more questions on this his talk today, his fascinating talk today. So yeah, I hope nobody is feeling shy, and I mean everyone should also try to go ahead and ask him some questions. Yeah, so it's okay. I'll try to ask one. Okay, I hope people will not mind my asking one question. So, I mean, this is coming from Segon's question just a minute ago. So you're feeling that if we want to talk about vortex entropy, we should not really try to calculate the vortex entropy of single vortex in a situation which is in the background of some constant supercurrent flow. Is that, I mean, am I getting this correct? So what would be like the discrepancy coming out from this kind of approach?
So very good question. So you know, I think the problem should be decomposed, because I think the Behnia story is correct. So the whole point is not revising the fundamentals. It is just to see what are different. One is that you have electromagnetic energy and thermal energy. These two things are separate, as Sergey and all already noticed. The second point, which is very important, is that when there is an entropy in the normal core, it doesn't mean that this entropy in the normal core is attached to the magnetic flux line. The vortex is a complex object. It has a normal core. Inside this normal core, you have entropy, and it is a quantum of magnetic flux. Now, when you begin to move the system, what is moving actually is the magnetic flux. Of course, the core moves with the magnetic flux, but during this movement, if you write actually the equations, you see that actually the core is not some rigid stuff which is moving just steadily with the flux line, because it is not that movement. It is not the movement of the normal core which gives you the electric field. It is the movement of the flux line, the magnetic flux line. So what makes the problem difficult is to be able to disentangle these two things. And just to make that, it is not Nernst effect which is only mysterious. The Hall effect in superconductors sometimes changes sign. And there has been literature, but these people were aware of that. And they have written different ways of saying that, okay, there is not only Lorentz force, you have also Magnus force, and then it creates some possibility that vortices don't give only, you know, this sign, but another sign. Because normally the movement of vortices normally is dictated by electromagnetism. Here, the problem is a thermodynamic problem. It's not just electromagnetic. So it's a bit different. So I think it is the beginning of, you know, again, the field was considered closed, but it is not closed. It's completely open to new ideas.
Okay, thank you very much. So yeah, any other questions or comments? Yeah, I mean, it was not only a fascinating talk, but the result has been very surprising on very elementary level. So I guess everyone should go try to reflect on what was presented today, what has been presented today. And yeah, thank you very much for your talk, Professor Behnia. It was a
Thank
really
you for your-
fascinating one.
Thank you for your invitation and for your attention. Thank you.